So what this chapter will cover is, remember, if you refer back to my chapter 1 slides, you'll see that I'm saying that you should know like the role of electrons in bonding. Well, this chapter goes like super deeply into electrons and quantum mechanics. But don't worry, I'll break it down. If it were that easy in the textbook, I would have just gone off the textbook. So this chapter will mainly cover stuff like introduction to quantum mechanics, atomic orbitals of hydrogen, spin, and some miscellaneous items that I will get to. So here's a little history lesson. So the image you see on screen right now is conference consisting of like some of the smartest people in all of science. But specifically, we want to focus on this guy, Niels Bohr. Now, what did he do? Now, first, I want y'all to watch a video of one of my favorite roller coasters. I've personally ridden it, and my god, it's a real doozy. Now, in quantum mechanics, Bohr introduced the idea that electrons can only take up quantized energy levels, meaning that they can only be restricted to these certain energy levels. Like, for example, if you've ever driven a car before, you know that once you start up the car, you're in parking mode. You're gonna have to switch gears into like reverse in order to, get out of your parking spot. So basically, this is like an illustration of quantum mechanics. And these energy levels, these are also denoted by the principal quantum number n. Those are especially useful later. So now we're going to get onto wave functions. I'm not going to get too much into the math because, to be honest, you can find all of the math simply in the textbook. And I don't want to mention all of that right in here in these slides. Well, interestingly enough, electrons do have wave-like and particle-like properties. And quantum mechanics hones especially onto that wave aspect. So basically, using this wave aspect, we can deduce that electrons can exist in like sort of clouds that describe the probability of finding an electron in a certain location within that cloud. Now, the wave function gives us a way of working out the probability of finding an electron in 3D space, with the wave function denoted by the Greek letter psi right here. Side note, for the probability density, which is the wave function squared, the wave function is multiplied by its complex conjugate. But in this textbook, we will just say that the wave function is squared. We'll mainly talk about complex numbers in quantum mechanics, more so in later chapters. How do we actually deduce these wave functions and energy levels? So what we use is something known as the Schrödinger equation to work out these wave functions. So right here, this I component is the imaginary unit, and this h with the bar is the reduced Planck constant. And right here, you have some special bracket notations, and you have your partial derivatives. This h represents what is known as the Hamiltonian of a quantum system, basically all the energy. But basically, because you have that I, that imaginary unit in there, that's why we have to multiply the wave function by its complex conjugate in order to get the probability density. So right here, we're going to introduce electron orbitals, and from here and like so on, we are only going to talk orbitals that belong to the hydrogen atom. And this is mainly because the hydrogen atom has only one electron, and this simplifies the picture for us. So, from basic science, we know that opposite charges attract, and there are favorable interactions between the single electron, which is negatively charged, and the positively charged nucleus. So what we use here is known as the Coulomb potential, and it describes the potential energy of the electron as varies. So right here, I use one of the greatest graphing calculators of all time, Desmos, to visualize the Coulomb potential. So I only graphed it on the positive x-axis because you can't have negative distance from the nucleus. So these x-axis units and y-axis units are more so just arbitrary. So you can see how it quickly goes down the closer and closer you get to the nucleus. So that's what the Coulomb potential is. What we do is, you see this kind of like shell right here on the electron orbital? Basically, this shell is created to encompass 90% of all electron density. So the shell just gives us a clear, rigid picture instead of like a fuzzy electron cloud. So the wave function for this 1s orbital is, this basically depends on a parameter named r, which is the radius, and this n constant is just a normalization constant times the exponential function, or we can just denote this as e to the power of negative r over a0. So you can see how we can kind of use Coulomb potential right here. What this a0 thing is, it denotes the Bohr radius, which is the most likely radius at which an electron can be found from the nucleus in hydrogen. And this is around 52.9 picometers. We do have a function that we use known as the radial distribution function, which basically models the probability of finding an electron as a function of the distance from nucleus. And here's a quick little side note. Whenever we're building like these electron orbitals, we think of the nucleus as just like a single point. And this actually checks out in real life because like from actual experiments, aka the Geiger-Rutherford experiment, we know that the positively charged nucleus is like super concentrated in the middle of an atom. So that's why we treat the nucleus as a single point when we're talking about orbitals. Now, we're going to be talking about the radial distribution function of the 1s orbital. So the 1s orbital is a simple sphere, and what we do for this radial distribution function is we set it equal to 4 pi r squared. So 4 pi r squared is just the surface area of a sphere, and it's times the probability distribution, which is just the wave function squared. So here's an illustration of the textbook of how RDFs are constructed. So right here, there's already a description, but I'll break it down. So this first plot talks about, just the simple wave function. This green line denotes the wave function squared, aka the probability distribution. And since 4 pi is just a constant, we can just model this red line as r squared because that's the only variable. And we can see right here from like a combination of these two, we get this kind of curve that shows the probability of finding an electron as a model of the radius. And as you can see, the Bohr radius has the highest peak. And this matches perfectly because the Bohr radius is defined as the most likely radius at which you are to find an electron from the nucleus in a hydrogen atom. So now we're going to go on to quantum numbers, which should be simple enough. So there are 4 main quantum numbers that you'll need to know. So the first one is the principal quantum number, denoted by n, which I already told you at the start. And n has a range from 1, 2, 3, and so on. And the names for the shells denoted by n goes like this. So if n equals 1, we will have the K shell. If n equals 2, we will have the L shell, and so on. So we're just going to follow alphabetical order. And the second quantum number that we will need to know is known as the angular momentum quantum number, which is denoted by L. And this has a range of integer values from 0 to n minus 1. And what the use of this is actually, the use of this is that L actually shows which kind of orbital group it is. So there are 4 main orbital groups that you'll need to know: S, P, D, and F. So those are the 4 main orbital groups. So a value of 0 for L represents the S orbital group, 1 indicates the P, 2 indicates D, and 3 indicates F. And there are some theoretical orbital groups such as G and I orbital groups, but they don't actually matter in this scenario too much because you won't actually be interacting with them too much. So the fourth quantum number that you'll need to know is the spin quantum number, and this takes values only, that is negative 1/2 and positive 1/2. So those are the only two values that spin can take. And we'll get to the experiment that actually proved what spin is later on. And also, we have our individual orbitals in these orbital groups, and each individual orbital only holds 2 electrons, and I'll get to that explanation later. So here's some quantum numbers in practice. So right here is my favorite orbital group of all time, specifically the 2p orbital group. And we want to specifically focus on the first individual orbital. We're not talking about any specific individual electron, we're just talking about a specific individual orbital. So, we're dealing with the 2p orbital group, and just by looking at the 2p part of that, we can see that right next to the p, we have the number 2. So what this indicates is that this set of orbitals exists at n equals 2, which is the L shell. And using the definition of the quantum number L, which is the angular momentum quantum number, L can either be 0 or 1. And a value of 0 for L would mean that this would be an s orbital group. But this is a 2p group, not a 2s group. So L is 1. And right here we have the magnetic quantum number. It takes up values from negative L to L. And they actually denote the individual orbitals in order. So you see how neat that is? So we're talking about the first individual orbital. So the magnetic quantum number is, I accidentally put negative L there, but the magnetic quantum number is negative 1. So now we're going to move on to what orbital energies are. What orbital energies describe is basically how much energy does an orbital have. And remember, we're only talking about the hydrogen atom, which only has 1 electron. So this equation that I've done here is only for 1 electron species. So the equation for the energy of an atomic orbital group is negative z squared times the Rydberg constant over n squared. So z is just the atomic number here. And right here, the Rydberg constant is 2.18 times 10 to the negative 18 joules. And we can simply plug in our values for that. And as long as it's just a 1 electron species, it'll always be precise. So that's what the equation is. And also, here's something neat. You see how the Rydberg constant is denoted by RH? The subscript H stands for hydrogen, and since hydrogen only has 1 electron, that would automatically, delineate the use case of this equation. So now we're going to move on to the concept of what degeneracy is. So, in the equation of orbital energy, the only quantum number that we really get a mention of is n. So there's no mention of L, which actually denotes the different orbital groups, S groups, P group, D group, F group. And this means that as long as you have these groups of orbitals in the same energy level, aka having the same value for n, they're all different, but they have the exact same energy. And if we see this, we say that these orbitals are degenerate. However, in multi-electron atoms, this degeneracy is lost. So that's the quick thing to look out for. So now we're going to go on to the 2s orbital. So the 2s orbital is still spherically symmetric, but there's something a bit off here. Wait, let me zoom in for a second. So we get like some kind of cavity here, and it appears to be a circular cavity. So that area is known as a radial node. And nodes are regions where there's absolutely zero chance of finding an electron. And there are also angular nodes. So you can see this radial node-like region actually is like a circle. So next we'll go on to, as I said, my favorite group of orbitals, the 2p orbitals. So the reason why I like them so much is because they're not boring at all, but they're not super complex neither. So there are 3 individual orbitals that are in this group: 2px, 2py, and 2pz. These x, y, and z indicators just talk about what axis they align on in 3D space. And there are angular nodes that are present. And so what angular nodes are they're basically the same thing as a radial node in the sense that the probability of finding an electron there is absolutely zero, zilch, nil, however you want to say it. However, the difference from a radial node is that angular nodes exist as a plane, aka like a sheet, these areas of like finding an electron. And if we go back to the 2s orbital, we can see that the radial node here actually looks like a circle. It looks like an empty circle, like separating these two regions. So that's what the main difference is. And the reason why it's named the angular momentum quantum number is actually because of this, these angular nodes, and also there will be mention of angular parts later on in the slideshow. So right here is another good side note that I want you guys to know. So I keep seeing this in textbooks from time to time, and it's about time I stand up for this. So do you guys see this image? Wait, let me zoom in again. Yes, right here. If we look at the past image, right here for reference, we can see that the p orbitals look like 2 more so squashed spheres. But in this image, we get like a figure 8 kind of shaped. So just remember, you have to be careful when seeing this, as this does not properly represent the shape of the 2p orbital. So the math behind all this. So let's go back to wave functions. And these wave functions consist of 2 parts: a radial part, which relies on a parameter named r, and an angular part, which relies on 2 parameters known as theta and phi. And remember when I said that the 1s orbital is a perfect sphere? Yes, this is because the only parameter that the wave function relies on is r, and this has no reference to either theta or phi. So unfortunately, we are back to radial distribution functions. So now taking this into account, that wave functions consist of a radial and an angular part, we can infer that the RDF for an orbital only requires the radial part as a section of the equation. And we can actually extend the notion of RDF to all orbitals that are in the hydrogen atom. And what we will do is this function p, which denotes the RDF, this RDF is equal to r squared, remember r is the parameter here, times the radial component of the wave function, which only depends on r2, squared. Using this equation that I gave you, we can see that, interestingly enough, the 1s orbital actually has its electrons bound way more tightly to the nucleus. And by way more tightly, I mean way more tightly. More than 2s and 2p orbitals. However, the RDF talks about the probability of finding an electron in the thin shell. And we're talking about like the volume that's underneath this thin shell. And volume grows super quickly. So that would explain why the 1s orbital has its electrons bound way more tightly than the 2s and 2p orbitals. We're finally done talking about these boring radial components. Now let's get to the angular components. Now these angular components, as I said, rely on 2 parameters, theta and phi. So right here I have listed the trigonometric functions that actually show the angular part for these orbitals. Now right here is using these trigonometric functions. These functions actually act as like an outline for the orbital. And so we can see that theta had the start and end point, which is 0 and pi, on the z-axis. So right here. And it arches onto the x-axis. And as for phi, it runs along a circle on the x and y axes, with 0 and 2 pi being its endpoints. So we're going to move on to the 3s orbital. This has one more radial node than the 2s orbital. As you can see, there are two spheres, sphere-like regions, I can say, where the probability of finding an electron is 0. And right here we have the 3p orbitals. Not only does this have one angular node, but it also has a radial node, because as you can see in these images, there's another sphere-like region where the chance of finding an electron actually is 0. So now we're going to move on to 3d orbitals. Now these are actually interesting orbitals, more so because the transition elements, your favorite metals like iron, nickel, titanium, and my personal favorite, palladium, they all occupy these orbitals, these d orbitals. We can actually see, like, from the first one, this is denoted by 3dz squared, it actually seems to have cones for its two angular nodes, interestingly enough. In fact, what we can do to figure out the angle at which these cones originate from is we can use just the angular part of the wave function for this orbital. And so what we can do, since we have this angular part, which is 3 times cosine squared theta minus 1, we can set the wave function value to be 0. And through some algebra, and make sure your calculator is set to degrees and not radians, the angles are 54.7 and 125.3 degrees. So that's actually like a neat example of using the angular part of a wave function. So here's just a general picture on nodes. So the total number of nodes is n minus 1 in an orbital group, and the total number of radial nodes is n minus l minus 1, and the total number of angular nodes is l. So the reason why they include angular in the name for L is also because of this. And so this is just a small exercise. I'm just going to show the solution in a bit. So we're just going to focus on this specific orbital. So I want you to tell how many nodes are there in total and how many radial and angular nodes are there. So I'll just skip to the solution. This is the 4f orbital group. So the total number of nodes in this orbital is going to be n minus 1, which is 4 minus 1, which equates to 3. And right here, the equation for total number of radial nodes is n minus l minus 1. Now, for an f group of orbitals, L is set equal to 3. So for 4f, we have 4, which is n, minus 3, which is l, minus 1, which means that we have 0 radial nodes. And the total number of angular nodes is denoted by L. And since we already know that L is 3 for f orbital groups, this means that this specific orbital has 3 angular nodes. So that's actually something neat that I wanted you to know. And what do we see right here? We see 3 angular nodes, which are again planes that separate these areas of like actually finding an electron. So next we're going to move on to the concept of what spin is. So spin is actually an interesting phenomenon, as it's the last quantum number that I've actually introduced. And this can only take values of either positive 1/2 or negative 1/2. And in fact, spin describes a sort of intrinsic angular momentum that electrons have. Now, I won't get into like the physics of like angular momentum, but it's just how at an angle a particle travels. So that's what spin describes. Now, how spin was introduced is introduced through the Stern-Gerlach experiment. So basically, these two guys got some silver atoms, and they're like, you know what? We're just gonna treat these neutral silver atoms like just a big neutral electron, because charge is able to get into the way of their experiment, and electrons are negatively charged. And so what they did is they sent these atoms through a magnetic field, and then they found out that these atoms are actually split into 2 groups, And this shows that angular momentum is quantized, like energy levels, in elementary particles such as electrons. If you go on to study something like particle physics, spin will be mentioned. And the concept of spin is especially important in multi-electron atoms. Now right here's an illustration of spin. We have our spin up and spin down. And we can see these electrons as particles. One of them seems to be going up, one of them seems to be going down. And they're actually like spinned at an angle. Like for example, if you've ever played like cricket before, which I have, you can actually apply not only just like a forward force on the ball when you're bowling it, but you can also apply like an angle to it. So once it hits the ground, it travels in that direction at which you put the angle at. So I think that's a good analogy for spin. Now, we've mainly just been talking about hydrogen, but we can also extend this notion of atomic orbitals in hydrogen also to hydrogen-like atoms. Now, these atoms only have one electron like hydrogen. So, using this equation for orbital energy now on for hydrogen-like atoms, since the nuclear charge is increased, the energy of the orbitals become more negative. As you can see, Z is part of the numerator, and as the numerator increases, you'll get a more negative value for what you're evaluating. And you can see it right here in this illustration. Now we're going to go on to multi-electron atoms. So for now, we've mainly just talked about the atomic orbitals that are present in hydrogen. And the reason why we picked hydrogen is because it only has one force in the atom. Just the attraction between the positively charged nucleus and the negatively charged electron. So we just mainly did that for a more simple picture. Now, for hydrogen, using the Schrodinger equation, because there's only one interaction, we can solve the Schrodinger equation analytically, meaning that we're able to find the precise mathematical functions. And going on to spin its role in multi-electron atoms, we get something known as the Pauli exclusion principle. And it states that no two electrons can have the same quantum numbers, which means that each individual orbital can only occupy 2 electrons. Going on to multi-electron atoms, let's take helium for example. Helium has 2 electrons that are both in the 1s orbital. Now, since like charges repel and opposite charges attract, this will cause electron-electron repulsion. And from this, we get an extra force added, which means that we can only solve the Schrodinger equation numerically, which means that we have to like quote-unquote eyeball the solution to arbitrary precision. Learning from this, because of this electron-electron repulsion, the 2s orbital in lithium has a different energy from the 2s orbital in hydrogen. And we're talking about like neutral lithium atoms. Now we're going to go on to electron configurations. The order in which electrons are filled in is governed by the Aufbau principle, which comes from the German word for building up. So s orbitals only hold 2 electrons, p orbitals can only hold 6 electrons, d has 10, and f has 14. Now, using the Pauli exclusion principle, we can just simply deduce that. Since we know that s groups only have one individual orbital, p has 3, d has 5, and f has 7. So we can just use the Pauli exclusion principle and just multiply that by 2. And we can simply just use this table to determine in which order electrons are filled up in. It's actually very neat, in my opinion. And now we have an update on orbital energies. So in this section, we'll introduce the concept of screening, which is basically what happens when electrons in the lower shells actually act like somewhat as a shield to that attractive interaction between the nucleus and the outer electrons. And so what this creates is a need for an effective nuclear charge, which is denoted by ZF. And this, how I'll word it at least, is what the quote-unquote real charge is on the nucleus for the valence electrons. It's like the actual feel like for the outer electrons. And so we can substitute this into the orbital energy equation, which now replaces Z for ZF. And using some algebra, we can simply deduce the effective nuclear charge, which means that it's just the square root, and I have the equation right here. It's the square root of negative n2 times En over the Rydberg constant. Now En is just the orbital energy, and this orbital energy is in joules, of course. So we're going to go on to what penetration is. the penetration effect just talks about how close an electron can get to the nucleus. And the trend is s orbitals over p orbitals, which are over d orbitals, which are over f orbitals. So if we have two orbital groups in the same energy level, like take 4s and 4f, we would surely expect the 4s electrons to be closer to the nucleus than the 4f electrons. So that's what penetration describes. So we're about to close this up, so I want to talk about what ionization energies are. So the ionization energy of an element is the energy that's required to remove one valence electron from an atom that's in the gas phase. But it can just be thought of as the energy of A plus, which is the ionized version of atom A, minus the energy of A. And for one electron atoms like hydrogen, the ionization energy is just the negative of the orbital energy. So that's a simple equation that you can just use. You can just pull out the orbital energy for your one electron species, and you can just flip the sign on it. And from there, you'll just get the ionization energy. Unfortunately, for multi-electron atoms, instead of IE being equal to negative En, we have to put the approximately sign instead of the equal sign. But it is still a really good approximation. Now, this rule, known as Koopman's theorem, is true if the orbitals for the ion are the same as the orbitals for the neutral atom. So that's what ionization energies are. We'll go back to the concept of spin. Remember when I said that spin will be useful in multi-electron atoms? Yes, this is the section where spin becomes important. So this is known as Hund's rule. And Hund's rule states that electrons will fill up these degenerate orbitals singly with the same parallel spin before pairing up with these spin downs. So that's what Hund's rule describes. So I think generally, for an example, after like a long grueling day at school, me and my friends were just like excited to get on the bus and chat. So generally, we all like to have our own seat with great legroom before we have to sit next to each other. So that's a good analogies for Hund's rule. Going back to ionization energies, we're finally about to close up. So here are some exceptions to ionization energies. Generally, I used to think that ionization energies would always increase as you go along a period, which, yeah, that would make sense. However, there are two exceptions in the second period of the periodic table that I want you to know. So there's a drop in ionization energy from beryllium to boron, because boron has only one p electron, one 2p electron, and because of that electron being added, the orbitals that are now before it are screening. And there's a drop from nitrogen to oxygen because of electron pair repulsion. So what did we mainly cover again? We talked about introduction of quantum mechanics, the atomic orbitals of hydrogen, spin, then we talked about hydrogen-like atoms, multi-electron atoms, and ionization energy. Now, of course, there's a lot more, like radial distribution functions and whatnot, but you can always refer back to these slides. These slides will be later on published. So that's just it. That's the end. And here, there's a little sneak peek. The next chapter will talk about molecular symmetry. I know symmetry might seem useless, but this will heavily set you up for the next chapter.